Okay, so conjugated dienes. I noticed that I start all my videos with the words okay, or the letters okay, and I don't know how to stop that. I'm going to try with the next one. It's too late for this one. 17.2, conjugated dienes. Okay. A sterically hindered base can be used to form dienes, right? So how are you going to make dienes? Well, you can make it with a sterically hindered base, which, for example, terbutoxide, right? So potassium terbutoxide. Potassium and terbutoxide looks like this. Right? That doesn't look sterically hindered, but don't forget, these are 3 methyl groups. This is huge. Okay? Oops, there's a minus on here. Circle that plus to make it look even. This is the base, and it is huge. Okay? So, that makes it that if we're going to do an elimination, we're not likely to come in and get that hydrogen, but instead we're more likely to come and get one of these hydrogens right there. So watch this. Zero. Bump. That's patronizing, isn't it? No more sound effects. That's what we get, right? This is an E2. Elimination. And boom. Okay, so that's how we get that's how we get conjugated dienes. You might start with an allylic bromine, or you can start with a dibromide. By the way, one student, John Sennett, is going to say, how do we get that? He's going to be thinking about this right here, and that's smart. How do we get that? Right? Because, I'm going to be saying, how do you make this stuff from this stuff? Okay, so practice with conceptual checkpoint 17.2. Let's talk more about conjugated dienes. So single bonds that are part of a conjugated pi system are shorter than typical single bonds. This is 148 pm. I was almost going to say picometers, but that's my question for you. What is pm? And this one's 153 picometers. So can you see that this single bond is shorter, right, by a couple picometers? Why? Well, there's 2 reasons. Number one, this bond right here is a single bond, but it's made up, right, from a carbon, from the overlap of 2 sp2 hybridized orbitals. This one is made up from 2 sp3 hybridized orbitals, right? And sp3 has more p character in it. More p. More p. Specifically 75% p, right? Can you see that? 3 p's, 1 s's, right? Means longer. Sorry. More p means longer. This has less p. What percentage p is this? Can you see it? 67%? Right? It's 2/3. Because there's 1 s and 2 p's. It makes it 67% p character. So that makes it shorter. But there's another reason why it's shorter, which we'll see in a couple minutes. Actually, I think in section 17.3, we'll see. It's 2 reasons why that bond is shorter. How much shorter? Well, 4 picometers. How do you spell 4? 4 picometers shorter. Okay. I mean, it's not a big difference, but it's more than 1% shorter. The bigger things actually are coming up next. Next after this page. So the more S character a carbon has, the shorter it is, right? So I said here, the more P, the longer. Where am I here? The more P, the longer. Conversely, the more S character a carbon has, the shorter its bonds will be. Why? Well, because an s orbital is spherical, right? A p orbital is long. So if it's sp3, if it's hybridized, it's going to be shorter than a p, but also it's also going to be more spherical, right? So sp3, can you see that's 25% s character? Or 75% p character, right? This one's 67% P, which is what I said in the previous slide. Can you see that? And can you see it's also getting more spherical? Okay, so you have two nodes here. I'm sorry, one node, two lobes, right? You still got your two lobes, but one's becoming more spherical. Well, they're both becoming more spherical, but one's becoming bigger and the other's becoming smaller. All right, so practice that with conceptual checkpoint 17.3. Now, this is super interesting. How do heats of hydrogenation provide information about stability? So what we can do is we can take two molecules of this and reduce it. What is this? I shouldn't say this. I'm on my canvas. I can name this, right? Sorry about the background noise. Got some noise going on outside. It's a beautiful day. I could not resist opening the windows. So 1, 2, 3, 4 carbons, right? So it's butane, and oops, I got a double bond here. So it's butene, and the double bond is between carbons 1 and 2. So it's 1 butene, right? Okay, so if I take two molecules of 1 butene and hydrogenate it or reduce it to butane, then I get this much heat out of it, 254, right? So what does that mean? All right, so this doesn't tell us much, but watch this now. If I instead do a molecule of 1,3 butadiene, if I reduce two double bonds like this, and this is cool, I get less out of it. I only get 239 kilojoules. Why? Why is that? Because this starts out with less potential energy. In other words, it's more stable. Oh, look at that. Please look at it. It really is helpful to think about this from a couple different angles. And in fact, this is excellent evidence that conjugation makes it more stable. Okay, so let me ask you a question before we move on. What would you expect if I treated both of these with 2 moles of hydrogen to get plain old hexane? What would you expect? I know my question's open-ended. I want you to think about that. What's a good question, right? What should I be asking? What would I be asking with something like this? What's the point? All right. So, rank the following compounds in order of increasing stability. So what I'm going to do is I'm going to look for conjugated dienes, or conjugation, right? Turns out I've got sp2, 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 sp3, dead end, sp3, dead end. Okay, 4, watch this now, sp2, sp2, sp3, dead end, sp3, okay, dead end. All right, so I only have 2 there, no conjugation there. sp2, 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 sp2. These are conjugated. Wait a second, this looks identical to that one, doesn't it? There's an sp3. No, it's not quite identical. Okay, but watch this. sp2, 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 sp2. Wow, look at that. Beautiful. 6. Okay? 6 of them. So, rank the following compounds in order of increasing stability. Can you see that? Okay, bring your answer to class. All right, in general, single bonds freely rotate. You know that. You've seen that before. If we have butane, this bond can rotate, right? And then it can swing all the way back around. Still going, right? So there. Still going, right? This guy rotates freely. When we talked about this before, we used Newman projection formulas. Remember these? Newman projection formulas, where this shows a dihedral angle, and these guys were rotating constantly. Now, granted, there was some resistance to rotation when we get eclipsed. Remember that term? When we get eclipsed conformations, but they did freely rotate. Okay, now the two most stable rotational conformations for butadiene are S-cis and S-trans, right? Where that's rotating. Okay, however, they don't rotate freely. Why? Because of the conjugation. We'll see more in section 17.3, but it turns out this is evidence that there is double bond character. Wow, surprise. All right. So the S-cis and S-trans both allow for a full pi system. So you get side-to-side overlap, side-to-side overlap, right? See that? Side-to-side overlap, side-to-side overlap, side-to-side overlap, side-to-side overlap. Watch this. Side-to-side overlap, side-to-side overlap still, okay? That's why the conjugation's so good. However, the picture's not shown here. When this thing, when it rotates, as it rotates, that conjugation is broken. Must interrupt conjugation to rotate. How do you spell rotate? R-O-T-A-T. You must interrupt the conjugation to rotate. Can you see that? If I turn this guy around and rotate about this bond right here, that's going to be broken. Okay, so look at this. Look at this. If you have the pi system here, see this all conjugated perfectly. As it rotates, these pi. Let me draw them. I'm going to exaggerate them a little bit, okay? Right? They're all. Can you see an unhovered sp orbital here? Unhovered sp orbital here. Unhovered sp orbital. Unhovered sp orbital. Side-to-side overlap. Let me do a different color. Side-to-side overlap gives a pi bond. Right? Side-to-side overlap gives a pi bond, but there's also some conjugation right here, right? As this turns around, can you see my writing? As that turns, these are no longer parallel then, and you get an increase in energy. And this is called, really, this is literally an activation energy. Even though we don't have a reaction here, we do have a process going on, and that's an activation energy. And that activation energy is 15 kilojoules per mole. Wow. Look at this. Just let me go back. Go back for a second. Look at that. What? Just one second. I got a friend here who's showing me something. Oh, I didn't put out that question. What does the S? Is that what you're asking? Yeah, what does the S in S-cis and S-trans stand for? I'm not going to tell you. I Googled it. It's the top hit. It's a little bit of a trivia. It's just there to help you. These kind of questions, Klein or Wiley does this for us, and I'm glad they do. I'm glad they ask us these questions, but these are thought-provoking questions. They're going to help you appreciate things more. So go Google that. See what S stands for. It's the top hit. At least it was the top hit on June 1st. Okay, so where are we here? Why is S trans lower in energy? Another good question for you. It is lower. Why is it lower? And what does that mean? How much lower? Well, it's 12 kilojoules per mole lower, but watch what this means now. With this barrier, with this 12 kilojoules per mole, look at this, 98% of the molecules are in the S trans form. Right? That's probably at room temperature. If it was really hot, it would be 50-50. I mean, if it was extremely hot, it would be 50-50. But at cooled temperatures, 98%, and I would say at room temperature probably. Okay, 90% are in the S-trans conformation. Okay, hope that's helpful.